you a reminder that it's close to 5 minutes of overlap. Got it?
Yeah.
Yeah. Yeah, you can start your presentation, Likhitha.
Are you able to see my screen?
Yes, yes, I can.
Okay.
I can able to see.
Yeah. This is Likhitha, and my capstone advisor is Professor Tejan Kim. Today, I will be presenting my capstone project, Security Risk and Guardrails in LLM, a practical analysis of LLM vulnerabilities and safety mechanisms. Uh, this project focuses on identifying major security risks in LLMs, including prompt injection, attacks, data leakage, harmful content generation, and hallucination. To address these risks, I developed a guardrail-based security framework using AWS services. The goal of this project is to improve the safety, reliability, and trustworthiness of LLM-powered applications. This is the agenda of my project. Let's begin by looking at the problem statement and understanding why security is an important concern of LLMs. LLMs are widely used today, but they have security risks. These risks include prompt injection attacks, data leakage, and hallucinations. These issues can lead to unsafe or incorrect responses. The main question of the project is how to identify these risks and reduce them using guardrails and security mechanisms. Now that we have identified the problem, let's look at the motivation behind this research and why solving these security challenges is important. The motivation for this project comes from the growing adoption of LLMs in applications such as customer support, virtual assistants, and content generation systems. This model help organizations improve efficiency and automate many tasks. However, despite their benefits, LLMs can sometimes generate unsafe, misleading, or incorrect responses. They may also be vulnerable to security threats. These challenges can reduce user trust and create risks for organizations. Therefore, there is a need for effective guardrails that can monitor, validate, and control model behavior. This motivated me to develop a practical framework that improves the safety and reliability of LLM based applications. To better understanding these challenges, let's first review the background of LLMs and the security issues associated with them. LLMs are transformer-based AI systems that are widely used for tasks such as chatbots, question answering, and content generation. Although these models are powerful, they have several limitations. One common issue is hallucination, where the model generates information that is incorrect or unsupported. Another challenge is bias, which can occur because models learn patterns from large training datasets. In addition to these limitations, there are important security concerns. Prompt injection attack can manipulate model behavior through malicious instructions, while data leakage may expose sensitive information. Researchers have proposed solutions such as alignment techniques, human feedback, and risk management frameworks. However, many of these solutions focus on individual problems and not fully integrated into a single security network. This gap in existing research led to the development of my guardrail-based approach. After understanding the background and existing challenges, let's review the related work and the research studies that influence this topic. This slide summarizes three key research studies that influence this project. The first study by BI focuses on constitutional AI and rule-based alignment techniques to make language models safer. Their approach uses predefined rules and AI feedback to reduce harmful responses. The second study by Bommasani, he provides a broader analysis of foundation models and identifies risks such as bias, misuse, lack of transparency, and system level vulnerabilities. However, it mainly provides high level guidance rather than implementation details. The third study by G focuses on hallucinations and improving the reliability and output models through evaluation metrics and grounding techniques. Although this studies important aspects of LLM safety, each focuses on a specific problem. This reveals a gap in the literature because there is no single integrated framework that combines security validation and output moderation also. But my project addresses this gap by implementing a practical guardrail based framework that combines these protections into single architecture. Based on the gaps identified in the literature, I developed a guardrail based approach that combines multiple security mechanisms into a unified solution. The next slide explain this approach. My approach was to first identify major LLM security risks. Then I designed a guardrail-based architecture with input and output validation, and also implemented risk scoring, hallucination detection, and monitoring features. The solution was built using AWS services and Python. After defining the approach, the next step was designing the overall architecture and workflow of the proposed guardrail system. Before explaining the workflow, I would like to briefly describe the layers of the architecture. The system consists of 5 layers: the presentation layer, where user interact with the application; the API layer, implemented using Amazon API Gateway; and the security layer, which contain input guardrails and risk scoring. And next one is the LLM processing layer, which uses Amazon Bedrock and Clade. The monitoring Next is the monitoring layer, which uses CloudWatch for logging and monitoring. And now let me explain how the workflow operates. The process begins when a user submits a request through the application. The request is received by API gateway and forwarded to AWS Lambda. Inside Lambda, the input guardrail checks the prompt injection attacks, PII, and Denny list keywords. The system then calculates a risk score and classifies the request as low, medium, or high risk. If the request passes the validation, it is sent to the Amazon Bedrock, where the cloud model generates a response. The generated response is then checked by the output guardrail for harmful content, hallucinations, and policy violations. If the response is safe, it is returned to the user. Otherwise, it is blocked or replaced with a warning message. To implement the architecture, I used Amazon API Gateway to create the chat endpoint and route requests to AWS Lambda. The Lambda function was developed in Python and configured with environment variables for the cloud model, guardrail ID, and AWS region. Also implemented local Denny list validation to detect prompt injection attempts such as ignore previous instructions and bypass safety. I also configured Amazon Bedrock Guardrails to detect harmful content, prompt attacks, and sensitive information such as email, phone number, social security numbers, etc. For LLM processing, I integrated Amazon Bedrock with the cloud model. The Lambda function calculates a risk score, classifiers as requests as low, medium, or high risk. Also implemented a hallucination warning mechanisms that detects uncertainty phrases like maybe or I cannot verify. For monitoring, I used Amazon CloudWatch to record events including requests received, input blocked, output blocked, hallucination warnings, and response return. Finally, the entire infrastructure was developed using AWS CDK, which automatically creates the guardrails, Lambda function, IAM permissions, API gateway, and CloudWatch resources. After implementing the architecture, the next step was collecting runtime data and monitoring information to evaluate the effectiveness of the guardrail framework. Unlike traditional machine learning projects, this system does not use a training data set. Instead, it collects runtime interaction data generated while the chatbot is running. The collected data includes user prompts, API requests and responses, risk scores, hallucination warnings, token usage information, and CloudWatch monitoring logs. The system also records important security-related events such as blocked requests, prompt injection attempts, PII detection results, etc. This collected runtime data was later used to evaluate the effectiveness of the guardrail framework and analyze the overall security performance of the system. This slide explains how the system was evaluated. To measure the effectiveness of the guardrail framework, I used several evaluation metrics, including detection accuracy, prompt injection detection rate, PII detection rate, response blocking rate, response time, error rate, and risk score classification. A total of 50 test prompts were used during evaluation. The testing dataset included 20 safe prompts, 10 prompt injection attempts, and 10 harmful content prompts, and 10 prompts containing personally identifiable information. These categories were selected to evaluate how well the system could detect security threats, block unsafe content, identify security information, and maintain reliable performance. The results show that the system performed well. It achieved 90% detection accuracy and prompt injection detection and PII detection. The system blocked
Likhitha,
95% of, yeah,
you have 5 minutes left.
okay. The system blocked 95% of unsafe responses and maintained a 96% API success rate with an average response time of 1.2 seconds. These results show that the guardrail framework successfully improved the security and reliability of LLM interactions. The findings helps what the evaluation results mean. First, the system achieved a 90% detection accuracy, which indicates that the guardrail framework was effective at identifying both safe and unsafe interactions. Second, the framework successfully blocked 90% of prompt injection attacks and detected PIA-related prompts. This demonstrates that the security controls were able to protect the LLM from common threats and prevent sensitive information exposure. The 95% unsafe response blocking rate shows that the output guardrails effectively reduce the risk of harmful or policy violating content being written to the users. Another important finding is that the average response time remained at 1.2 seconds with a 96% of API success rate. This suggests that security controls can be implemented without significantly impacting the system performance. Overall, these findings indicate that the combining input guardrails, output guardrails, etc., this can significantly improve the security, reliability, and trustworthiness of LLM application. I will now play a demo video to demonstrate how the system works in a real AWS environment.
This demo presents my capstone project.
Is it audible?
Yeah, I can hear you. Can you make it in full screen? Is it possible to do that?
No,
Uh,
I
you
attached
can.
a
What you can
video
do is
here.
like just okay. Yeah, then you
A
can
guardrail-based
resume.
Can I play this?
Yeah, sure, sure.
secure LLM framework developed using AWS services. The system improves LLM security through input validation, bedrock guardrails, risk scoring, output moderation, and CloudWatch monitoring. First, I will show the AWS CDK code used to deploy the infrastructure. The stack creates the bedrock guardrail lambda function, API gateway, endpoint, IAM permissions, and CloudWatch logging resources. And now I will show the deployed AWS resources. Here you can see the API gateway. The system exposes a post chart endpoint which receives user request. When the request is submitted, the API gateway forwards to the AWS Lambda. Here is the Lambda function that processes requests and interacts with the Amazon Bedrock. Now I will show the main Lambda implementation. This is the main Lambda function. It receives the request from the API gateway and controls the entire workflow. Now I will show the Bedrock guardrail configuration. The guardrail is configured with harmful content filtered, prompt detection, restricted topics, and denied words, and PII detection. Sensitive information such as and social security numbers, passwords, AWS keys, and credit card numbers can be detected and blocked. Now I will test the deployed API. I'm using the safe prompt first. Yeah. Here, this request here, if you see this request is allowed and returns a normal response. Now I'm going to text the prompt injection prompt. If you see here, the system detects the attacks and blocks the request. Now I'm going to test with other request. I'm going Now I'm going to give my SSN number here. Here also the system detects sensitive information and applies the sensitive security controls. Here you can see PII found, which is social security number, and also the score is high. Uh, Finally, here are the CloudWatch logs. The system records the events such as request received, input checked, input blocked, output checked, response, return risk score, etc. These logs provide the visibilities into runtime, activity, and security events. This demonstrates uh, that how the AWS CDK, API Gateway, Lambda, Amazon Bedrock Guardrails, and CloudWatch work together to improve the security, reliability, and trustworthiness of the LLM applications. Thank you. This demo presents my
Yeah. In conclusion, this project successfully developed a secure guardrail-based framework for LLM application. The system uses input validation, output moderation, risk scoring, and monitoring to improve security. The results showed that guardrails can reduce prompt injection attacks, harmful outputs, and sensitive information exposure while maintaining the good performance. Overall, this project demonstrates how multiple security controls can be combined to build safer and most trustworthy of AI application. While the proposed framework achieved positive results, there are still opportunities to further enhance the system. The next slide discusses potential future improvements and
Yeah,
extensions.
thank you. Thank you, Likhitha. I just like, yeah, like 1 more minute, right? It's already way past the time.
Yeah, okay. These are the future work of my project. These are the key references that supported this research and implementation. Yeah, thank you. Do you have any
So, I
questions?
have like, yeah, I have a couple of questions. My first question is, can you go back to the first slide of your presentation? I just want to like see the project name in the first slide.
It's okay.
This demo presents this demo pre-
Or like, can you tell about your project name and about your project name?
One second. Yeah.
Okay, so the project is security risk and guardrails in LLM, the practical analysis of LLM vulnerabilities and case mechanism. Got it. So
Yeah.
I have a first question. The first question is simple. So you told you are getting a real-time data, right? From chatbot, whatever thing is entered, you are getting a real-time data. It's not a standard training data set for your model to be trained. You are getting a real-time data. Uh, but
Yeah.
I
I'll
think you skip the part where how are you, like training your model? You didn't tell that like how did you train your real-time data model? I think that's kind of like important thing I would appreciate if you can go and say just like how did you do it?
uh, yeah. In Lambda function, like I'm invoking the Claude model. I'm using the Claude
Yep.
model. I'm connecting to that. So we'll get the responses based on that model.
Uh, yeah, no, no, no.
Based on the
That
model
is
ID, we can change yeah.
no, that is not my question. My question is simple. So you are getting a real-time data. How are you training that? With that data, how are you training your model? That's my question.
Like I am not training the data set here. I am not using any data set or I am not training anything. Just I am using a LLM. Uh, yeah, I'm using the model using Amazon Bedrock.
Okay, so that means like you are not training anything, correct?
Yeah,
So I'm just wondering then, what exactly, in which part you are exactly using your LLM?
can you come again?
So you told you're not training anything with your model, and can you
Like
explain?
I used already trained cloud model that available in Amazon Bedrock.
Oh, so yes, but you told that you are getting a real-time data, right? But then why did you
Yeah,
state that? Uh, okay, yeah, come again.
are you asking about why I'm getting the real time data?
So I remember you told you are getting a real-time data, but when I asked you, you told you're not training that data with a model. Then why aren't you getting that data? Like since you told you have a Amazon Bedrock and you are using it, using that model. So what are you trying to say? Can you explain that particular part? That's where I'm
Like
just missing.
my project collect real time runtime data. Like using during the user interaction. Whenever a user submit a prompt, the system captures the information, user input, and request timestamp, risk score, etc.
So what are you doing from
These
that?
are logged. Uh,
With that data, what are you doing?
like I am storing in the Amazon CloudWatch.
Oh, so you are storing it in Amazon CloudWatch. So you are not
Yeah.
doing anything like training your model or something like that. You're not doing anything, correct? You're just storing
Can you
the
come again?
real-time data. So you're just okay.
Yeah.
Also, Likhitha,
This also helps me to evaluate the Guardrail framework also.
okay. And the second question is, can you explain how are you managing the hallucination? Because I didn't find any part where you told you are managing it. You told there is a service which is managing it. Can you please explain what is the hallucination and why is it using
Uh,
why are you using in that project?
like how I'm managing the rule based. Like my project includes only
You can take
hallucination
your time. You
warning
can take your
mechanisms.
time. Mhm.
Uh, like I'm managing through a rule based detection mechanism. Can you
Okay.
understand?
Yeah, I get it. I get it.
Uh, and also using frames, uh, some phrases, I'm detecting the hallucination. Like maybe if the system sounds like that, what it will detect it as a hallucination, and it gives a warning.
Okay. So what you can do is I will give another strong foundation for this project. I think I had an idea. So what you can do is you can use LLM Council. What it does is basically, instead of managing the hallucination for, depending on another service in AWS, what you can do is you can build a local LLM Council. What it does is there will be a lot of models, AI models. So whenever you collected that data and you stored it somewhere, right? Which is like you told you are storing it somewhere. In order to, neglect that hallucination, you can use multiple models at the same time to get the optimized answer. So that it would be easy for you to reduce like literally negligence hallucination. You can manage it. Don't you agree with that point, which I told you?
Like I didn't get you what you are saying.
Okay. So what I'm trying to say is hallucination. Instead of, hallucination is something happens if the question so uh, The model doesn't know which is right or wrong. What it does is like a transformer thing. So it will give you the possible words, correct? So what you can do
Yeah.
is you can use multiple AI models like Claude, ChatGPT, Gemini, or like various models. What you can do is with that models, combined models, you can give the data so that it will try to refine it. So that there
Yeah,
you can
I
reduce the
included
hallucination.
everything in future work, like I included
Yeah.
this thing in future work.
Mm-hmm. Sure, sure. Okay, okay, like it. Do you have any questions you want me to like? You want? Do you have any questions to ask me?
No.
Okay, awesome. If you don't mind, like, can you share the GitHub? I mean, the code stage, and also the PPT, if you don't mind, in Teams channel.
Yeah, sure.
Thank you, Likhitha.
Thank you.
I think it's.
Oh, can I leave now?
Yeah, yeah, yeah. Sure, sure, sure. You can leave.
Thank